Okay. Then thank you for your interest in our presentation today, which is P4-based in-band telemetry for OSM-Orchestrated 4G, 5G testbeds. I'm going to present this together with my colleagues Andrés and my colleague Mah-Rukh. So first I will give you a short introduction of our project, and then I'll give the word to my colleagues. So what is the content of the talk? Of course, I will show you the motivation of why to do in-band telemetry. And of course, then I will give an overview over our testbed. Particularly, my colleague Andrés will present a bit of details about the RAN part, the radio access network part. And then my colleague Mah-Rukh is going to present details on in-band telemetry based on P4. And of course, we will show you a live demo. Well, what's the motivation of our work? We have 4G or 5G testbeds. And obviously, if you have such testbeds, you want to evaluate the performance, particularly also the performance from the perspective of the user, that is the user equipment. So of course, you want to do this for detecting problems, but also, of course, to see the performance of new features, of new applications, of new protocols, and so on. With OSM, of course, you can do the orchestration and also get interesting metrics already in OSM, collected via Prometheus and visualized by Grafana. Metrics which are collected by the NFVI infrastructure, the network function virtualization infrastructure, as well as Shutu. But of course, these metrics are not very fine granular. You can, for example, have counters for the number of bytes and packets transmitted or received, and for example, also counters for the amount of memory and such. But what is really interesting for the performance of the user perspective of using such a network is, of course, to have fine granular per flow performance metrics. You can do this with in-band telemetry, that is monitoring flows at a packet level, and particularly enhancing this information by adding additional metadata to the packets flowing inside the network. Have fine granular analysis of where additional delay is introduced, or where additional or where a packet loss occurs. So the idea is, of course, to have this as hardware independent as possible, and with P4 programming protocol independent packet processors, there is the possibility to describe such activity in a hardware independent way, is by having customized switches, customized by P4 programs, which in fact are off-the-shelf components. Currently this is software, of course, but in the future you can probably easily buy P4 capable switches from the usual hardware vendors and have the things done in hardware. At the moment, of course, we do the things in software. Well, before I go too much detail here, we want, of course, to show you a demo. So let me shortly introduce you a few details about our testbed setup. We are using OpenAir interface, which is, of course, known to the OSM community from the last Hackfest. So I do not have to do too much introduction here. It's in fact just the open source implementation of enhanced packet core for 5G as well as 4G. We are using at the moment 4G. And also the open source software for the user equipment, the InnoB part, which connects to the user equipment using SDR, software-defined radio boards. I will not go into too much detail here, but we have written, of course, our virtual network function to realize a packet core. And this is of course open source, and it has been presented already at a previous OSM Hackfest. So therefore, a very short introduction only. We have a basic testbed setup, which is in fact consisting of an enhanced packet core for a 5G testbed, consisting of VNFs for four components of the packet core. There is MME, HSS, SPGWC, and SPGWU. And this is of course orchestrated by OSM, with the videos running an OpenStack cluster and with Juju used also for telemetry based on OSM. But of course, we want to introduce also in-band telemetry. So we extended the setup to a little bit larger network. And my colleague Andrés is now going to tell you a little bit more about the run part.
Thanks. Hi. Besides the packet core orchestrated with OSM, we are connecting a radio access network, which is based also on OpenAir interface. Specifically, we are running one eNodeB, deploying one antenna port, 25 megahertz, which provides mostly 16 megabit per second downlink. The idea with the switches we are using here for doing telemetry is monitoring user data in two parts on the network architecture. We are placing one P4 switch between the eNodeB and the SPGWU, which is the gateway that allow us to submit packets from the RAN all the way through the IP network, and placing one switch there to perform inbound telemetry, and also another extra switch just outside the mobile network between the packet core and the IP network. The idea with these P4 switches, as the user data is encapsulated using PTP protocol, is to dig into these packets, encapsulated packets, perform their the inbound telemetry, which is further submitted to a collector to perform further data analysis and storage. So this is the main architecture we are testing in our demo, and then we're going to explain how we perform the P4 programming for the inbound telemetry. So I'm going to leave the pitch to my colleague Mah-Rukh.
Hi, I am Mah-Rukh, and I will explain like the architecture from the point of view of the transport network, like what our switch does and what type of information it collects, and that information is then cloned to the collector. So here is some scripts from our P4 egress control. So the first one tells about if the packet is cloned or not. We are cloning our packet to do telemetry on it. We do not want to put extra information in our regular packets. So at the egress control, it tells like it finds out first like whether it is cloned or not. If it is not cloned, then it makes a clone of it. And then within the egress control, it again checks if the packet is cloned. If it is cloned, then it performs some calculation on it. For example, if you are interested in finding out the number of packets of a flow, and if you are interested to find out if our packet is part of a burst or not, so that calculation is done again at the egress control in my program, and then that information is added to the outgoing packet, but to the cloned packet that is mirrored towards the collector. So here, once the packet is cloned, with this packet, we do not need some of the headers that are attached to the original packet. For example, the UDP outer header and the GTP header, we do not need it for the cloned packet. Instead, we need the GRE tunnel. We want to put our original packet within the GRE tunnel. And within the original packet, there is an IP protocol again. And with that protocol, we add the IP option header. And within that header, like the IP option header, we add our telemetry data, which is, for example, the switch ID, which is identifier of the switch through which the packet is passing through, or the number of packets of the flow, and similarly other information, whether it is a hitter or not, and other like switch related information. So this information is added to the cloned packet and it is transmitted to the collector. So what does the collector do? Okay, before going towards the collector, like this is the parsing method of the packet, which is done by the P4. So it has to read up like the packets, packet headers from the Ethernet header, IPv4 header outer, the UDP outer header, the GTP outer header, and the IPv4 inner header. And then it has to drop the UDP header and the GTP header from the cloned packet, and instead of it, it adds a GRE tunnel to it. And accordingly, it updates the IP headers lengths of both the IP header inside the tunnel and outside the tunnel. And along with the inside IP header, it adds the IP option header, which adds the telemetry information. So when this information goes to the collector has a script, Python-like script, which extracts information from the packet and then adds it into a CSV file for recording. So it is like a screenshot from one of the packet. So here you can see like the whole packet. There is Ethernet header, then the IP outer header, then the GRE tunnel. Then with inside it, there is original IP packet. And to that packet, I am adding like the IP option headers. So you can see like there is telemetry information attached to it that is transmitted by the switch. So in this way, we can collect the information from different switches and put it into a database for further analysis. I hope this will be clear, and I am giving the screen back to my colleague Thomas so that he can demonstrate.
Okay, just a moment. Now we are going to present you a live demo. So I switch to the web browser. So first, hope you can see now my screen, my web browser screen.
Yes, we do.
Okay. Well, of course, we are using obviously open source MANO for orchestration of our network services. And as I've said, we have virtual network function for the packet core, as well as an extended virtual network function for the packet core with the P4 switches, as well as also a virtual network function for a flex hand controller, assembling everything into a network service. And particularly, this is of course then instantiated in our OpenStack cluster. That is the virtual network functions for the enhanced packet core, consisting of the 4 videos, one video for MME, HSS, SPGWC, and SPGW, as well as 4 introduced P4 switches, as well as 1 flex hand controller. So looking at the user interface of OpenStack, you can then see that we have quite a lot of different video instances. So particularly with virtual network functions managed by OSM, it is of course easily possible to maintain multiple testbeds, for example, for multiple projects or multiple experiments. So it's quite convenient. But today, I do not want to introduce you too much into the detail of the virtual network functions, but I then give the screen to my colleague Mah-Rukh for a live demo of the P4-based in-band telemetry part. So could the session share please change the presenter to Mah-Rukh?
There you go.
Thank you. So
I guess we can't listen you. Is it only me or
No,
you have lost the audio?
I lost audio as well, so I think we lost her.
Yeah, we all lost.
Yeah. So Mah-Rukh, we can't listen you.
Yes, you're mute, Mah-Rukh.
Oh,
We see your mic as mute, Mah-Rukh. Yes.
Can
Very good.
you
Yeah.
hear the
Hello?
audio?
Yes.
Yeah.
Now.
Can you hear? Okay.
Yeah.
Okay.
Sorry.
So I think you have not heard about like this. So as explained by Thomas, we have this switch implemented in the form of a VM, and also our collector is in the form of the VM. So here, the data actually I am sending is through a UE towards the enode B, and it is actually pinging data towards a server. This data is transmitted towards the switch S1U, and at this we have a P4 program which actually clones the packet and sends telemetry information towards the collector. So here is the collector who is getting the information. So like the information that I explained in the slide, Ethernet header, then the IP header information, GRE tunnel, and then the original IP header along with it, the telemetry information. So here you can see like it is the switch ID information is transmitted by the cloned packet in the form of telemetry. So we have actually two switches as explained by Andrés, one at the S1U, so its ID is 1 and the other one has 2. And then the packet count of the flow, and then amount of time that the packet spends in the queue. It is actually the time delta. So, and if it is a hitter or not, so hitter is actually a Boolean variable which says if the number of packets in the queue is beyond a threshold, then this packet is a part of a hitter, else it is not a hitter, and so on. So it is done for every packet, and this information is then stored into a database, logged into a CSV file, which can be later on analyzed. So yeah, so this is the presentation and demonstration. And this is the end. Thank you.
thank you. I guess we are
This concludes
ready.
our presentation, and thank you for your attention. If you have questions, you can ask them now or maybe in the chat. Or, of course, you can also write us emails. Are there any questions? Any questions?
You can just write your
Nope.
questions in your chat. Sorry, Mark. Go ahead.
No, it's all good. We were looking a little bit behind the scenes at some of the work and operators that you've written with the charms and whatnot, and we just on behalf of the canonical side of things would like to offer our support in looking at the charms, updating them to the newer operator framework and whatnot. So just wanted to mention that one. Because it's exciting work that you've done.
So at the moment we have everything running still on release 8, but of course it is requiring some work to get it upgraded to release 11.
Okay.
So therefore it would be helpful to get possibly additional information for doing this upgrade process smoothly.
Certainly. And one thing to note, earlier today, actually, we were discussing as a community about the feasibility of long-term support of OSM releases, because as you might be aware, release 8 is no longer actively maintained. And it looks like we're achieving consensus around release 10 being designated as a long-term support. And that will then have, documented and tested upgrade paths to the next long-term support, which may or may not be 12. We're still deciding on what versions are going to be long-term support, if we're going to label them any differently to designate them as long-term support. But we've heard that from the community, and we're trying to address upgrades between versions as well.
This would be a really useful feature, because at the moment upgrading is some quite complex work to get everything running on a new release.
Yes.
Particularly, it would be helpful to also have easily the possibility to upgrade an existing installation. Particularly
Yes.
with keeping all the existing data, not erasing everything and starting from scratch.
Yeah. Yeah, the upgrade from V8 is a little bit more of a challenge, but that's something that you know, we'd like to help and assist with that as a community. So we're here for you.
It's very interesting.
Perfect. Thanks, Marek. Thanks, Thomas.